A few days ago, I was consuming some media, and one time it was listing some numbers and showing neat things about them. The number 1033 showed up, and with it, it showed this. 1033 equals 8 to the power of 1 plus 8 to the power of 0 plus 8 to the power of 3 plus 8 to the power of 3. And I'm not sure why, but it struck me as really cool. It was kind of like a narcissistic number, but tailored for a specific base, as in the exponent base, the number at the bottom. In this case, that would be 8. If you didn't know, narcissistic numbers are numbers that, when you add all of the digits to the power of the number of them, you get the same number. I know that might be hard to understand, so I'll give an example. 153 is the first narcissistic number with more than one digit. It has 3 digits, so doing 1 to the power of 3 plus 5 to the power of 3 plus 3 to the power of 3 gives the answer of 153. The main difference here was that the digits are the power and that there was an independent number as the base. The independent number is the n in n-narcissistic numbers, a term that I just coined. Now I'm sure I'm just giving another name to something already discovered by mathematician blah 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 in 18 whatever, but this was new to me, so I decided to look for more. Of course I wouldn't do it by hand. I coded something up to do it for me. The code is really short, just 10 lines, one of them being unnecessary and just to make it look good. I'll put it in the description, but keep in mind that the indents might be messed up. The way it works is simple. First, you set a value of n in the code. In this example, it's 4. It then goes through the digits of the number that is at in the loop, summing up n to the power of said digit, as is done with n-narcissistic numbers. At the end, it checks if the sum is the same as the starting number, and if so, then it prints it. Then the loop restarts for the next number. This program does all of that for a single number in a matter of microseconds. Alright, enough stalling. Now it's time for the results. For one narcissistic number, as of course 1 was going to be the only one. 1 to the power of 1 is 1, simple enough. I couldn't find any 2 narcissistic numbers up to 1,000,000, and I'm sure that there aren't any at all. Even with a number as small as 9,999, the sum of 2 to the power of all of its digits is 5 times too small. That would be 2048. Keep in mind that I checked every number smaller than that, which were the only ones with values small enough to be close to the sum of 2 to the power of their digits. The only 3 narcissistic number is really tiny. 12, which is objectively the best number ever, but that deserves its own video. 3 to the power of 1 is 3, plus 3 to the power of 2 is 9, which makes a total of 12. Like with 2, the value of the number gets too big for the formula. For example, with 99,999, the formula outputs 98,415, which is just shy of the value in question. Now I was really surprised to find that there were not one, but 2 four narcissistic numbers in existence: 4,624 and 595,968. If you do the sums, then you'll find that these are both correct. In theory, the limit is 1,000,000, which I calculated up to, so that is that. Up to 1,000,000, I could not find any 5 narcissistic numbers, but seeing that there could be some up to 10,000,000, I decided to waste 90 seconds of my life staring at my computer searching for it. And when I saw the number 3,909,511 pop up on the console of my Python program, I was glad that those 90 seconds weren't a waste. If you do the sums, then you'll see that it in fact is the same number. There were not any 6 narcissistic numbers up to 1,000,000, and after learning that they could go up to 10 times higher, I found out that there weren't any up to 10,000,000. That was the upper bound for them, though. It's so odd, this sense of incompleteness. Why are there 3 and 4 and 5 narcissistic numbers, but not 6? Maybe there's an out-of-this-world proof that goes through the Riemann hypothesis, the twin prime conjecture, the Collatz conjecture, and finishes out with finding an odd perfect number. I hope not, though, and it probably isn't. For the past numbers, I've definitely known that those were the only narcissistic numbers of that n, since I only had to compute up to 10 million at most, which did not take 2 minutes. Now for 7 narcissistic numbers, they could possibly go up to 100 million, and I'm not letting my computer churn out those numbers for 15 minutes, so I'll keep the search limit to 2 million. I went up to 10 million for those last two out of curiosity, but I'm not doing that anymore. Sadly, there were not any 7 narcissistic numbers up to 2 million, but I'm sure that there's an 8-digit monster out there that follows these rules. Now for 8, I wanted to see if 1033, the number that started this all, was in a league of its own, and as far as numbers up to 2 million are concerned, sure. With 9, it's of course 10, the second smallest n-narcissistic number in existence, beaten by only 1. Now for a speed round from 10 to 50. It's pretty dry until 16 narcissistic numbers, with 1,053,202 being the only one below 2 million. The next one after that is 25, with the relatively small 31,301, which is pretty impressive in terms of compactness. It might be a coincidence that these two are both squares, as in the n in the n narcissistic numbers, but maybe not. Hopefully, though. Very interestingly, there are 32 and 33 narcissistic numbers, the first consecutive ends with any narcissistic number since 8 and 9. They're the incredibly tiny 2,112 and the larger 1,224,103 respectively. And finally is the 37 narcissistic number 111, and at just 3 digits, it is the smallest one we've seen since the 9 narcissistic 10. Anyway, I hope you enjoyed this short video about this cool group of numbers that I discovered or very likely rediscovered. Again, the code is down in the description, and I encourage you to try to mess around with it to find new types of them, like for example, in base 12 or something. Bye and have a good day.